Hey everybody, Mr. Judson here. So we're getting to this spot where we've almost accomplished everything we need to accomplish, which is good. We need to learn how to solve equations when the variable is in the exponent. You know, we've done our guess and check method for a simple equation, but what if these get a little messy? How do I solve that equation? Okay. Anytime you see a variable in the exponent, it's always going to require using logs or natural logs. We'll always have to do that, okay? So we just need to be aware of that. The moment you look at this problem, you go, oh, this is going to involve logs, all right? So there's some steps that we have to follow. Remember, I told you steps can go on your note card. So, if you wanted to put these on there, that'd be fine. Step number one is you have to isolate the base and its exponent. Okay? Remember, when we write something like 2 to the third power, the 2 is the base, right? The 3 is the exponent. So what I need to do is I need to get the base and the exponent by itself. That means get rid of the 5. Well, algebraically, how do we do that? We subtract 5 from both sides. Or, as I've told you guys this year, you just move that over and do the opposite. It's the same result. So I'm going to get 4 raised to the x plus 1 equals, if I move that 5 over and subtract it, I get 13. I have to get the base and the exponent by itself. It's got to happen. Okay? And so the next step, I don't know if you guys remember this. Well, I hope you do, because it's one of our basic rules in algebra, is when you're solving an equation, whatever you do to one side of the equation, you've got to do the same thing to the other. So if I add 4 to one side, I've got to add 4 to the other. If I multiply this side by 3, I've got to multiply this side by 3. If I take the log of this side, I've got to take the log of this side as well. That's doing the same thing to both sides. And so our second step is we want to take the log or natural log, it really doesn't matter which one you use, they both work, of both sides. Okay, so when I say take the log of both sides, what I mean is this. Log of 4 raised to the x plus 1 equals log of 13. I'm just doing the log of both things that are written here. And I don't know if you guys remember this. I told you of the properties that we learned. So we just did this the other day. Of the properties, the most important one is going to be where when you have a log of something raised to an exponent, you can bring that exponent down in front. See, I can't solve this until I get rid of the exponent. And that's the way that you get rid of it. Is once you have a log out in front, you can bring this down in front and then write it this way. X plus 1, put it inside parentheses, times log of 4 equals log of 13. Now, when you guys look at this, there's a couple things that we have to remember. First of all, when you say log of 4, this is just a number. I just got to grab my calculator and figure out what it is. It's a decimal number. And it's not uncommon for people right after we learn this to ask, well, what does that even mean? Remember, a log is an exponent, and what we're saying is whatever the base is, this is base 10, right, because there's nothing written there, 10 raised to what power equals 13? I don't know. I'm going to use my calculator to find it out. Or 10 raised to what power equals 4? I don't know, but it's just a number, right? It's just some number, some decimal number. So every time we see this, we have to think to ourselves, well, it's just a number. Okay? I'm not going to hit the calculator buttons yet because I want to wait till I get near the end. That way I don't have a bunch of rounded numbers. Okay? But if I wanted to hit the button right now, log 4, enter, and see what I get, I could do that. Write down 4, 5, 6 decimal places. Because that way when you move over and divide, even though you've rounded, you're probably still pretty close. Okay? What I'm going to do is I'm going to say to get x by itself, I first of all have to get rid of this, so I'm going to move it over and subtract, or divide, sorry. Opposite of multiplication is division. All right, so let's write down another step here. So after I took the log of both sides, I wanted to get the variable down in front. So move the exponent down in front. Okay, we're using our properties of logs that say you can move this down in front and then multiply those. All right, and now I just need to solve for x. So that's my last step. Solve for x. All right, so I'm going to move this over and divide. So what I have is x plus 1 equals log of 13 divided by log of 4. Okay, that's not one of our properties. Don't look at that and go, oh, dividing, all I got to do is 13 minus 4. That's not it. I need to actually punch this into the calculator. All right, so when I see that, I have to go log 13, close parenthesis, divided by log 4. Enter. So I get 1.850. So now I've got x plus 1 equals 1.850. Now subtract 1 from both sides. So when I move 1 over here and subtract it, I get 0.850. There's my answer. I have now solved that equation. You know, look at that answer, 0.850. I don't want to guess and check and find those every single time. That takes a long time. Doing this right here is what makes it go fast. All right? And you could check this if you want. You know, go back to the original problem, put 0.850 in there. So let's go back to our calculator. All right, I'm going to do 0.850 plus 1. There's my exponent. I'm now going to do 4 raised to that. So 4 raised to... Come on, go up there. Oh, this calculator doesn't do that. Sorry. Raised to the 1.85 equals plus 5. And there we go. I got pretty close to 18. I'm off by a little bit because I rounded this number, right? But we're going to have to do that. We're always going to have to round our final answer. All right, let's try another one. So one more thing, right here it says take either the log or natural log of both sides, okay? I could have used either one. Let's backtrack a second here and say, okay, if I would have done the natural log, and I had a natural log here, I would have done natural log of 13 divided by natural log of 4. And if we go back to our calculator and look at that, natural log of 13 divided by natural log of 4, 1.850. See, I would have got the same thing. Here's the thing that's important though, okay? Pay very close attention here. You don't want to miss this. If my base is E, the number E, remember 2.718? If my base is E, I have to use natural log. All right? I have to use natural log. Now, stop and think about this for a second. Okay, here it didn't matter which one I use. But sometimes I have to use natural log. Why not just always use natural log? If it matters sometimes but not others, why not just always use it? Right? That's what I'm going to start doing. I'm always going to use natural log of both sides. Even though the common log worked here, I'm just going to go to natural log. Okay? And here's why. Alright, so this time my base is E, so I have to use natural log. But my first rule still applies. I need to isolate the base and the exponent. I've got to get this part right here by itself. Okay? Now, remember, when you're solving, you do the opposite of the order of operations. I got to get rid of this number first. I got to do the adding or subtracting first, then I'll take care of my multiplying or dividing. Right? So I want to move this 25 over and add that. So I'm going to get 5 times e to the 2x minus 3. equals, let's see, 117 plus 25, that'll be 142. Okay, I still have my base and my exponent here. I got to get rid of the 5, so I'm going to move that over and divide. So I'm going to have e to the 2x minus 3 equals, let's see, 5 goes into there, 28.4, I believe. You guys double check that on your calculator, all right? All right, base is isolated, the base and the exponent. Now I need to take natural log of both sides. And I have to use natural log here because of the e. All right, so I'm going to say natural log of e raised to the 2x minus 3 equals natural log of 28.4. And then I want to bring my exponent down in front. And here's why you want to use natural log with e, is when you look at that, we've already talked about this, natural log of e is equal to 1, right? So really I could just get rid of that. 1 times anything is just the same thing, 28.4. And so this, again, when you look at that, it's just some number, right? I'm not worried about what that number is. I really don't care right now. But what it means is, if this is log base e, it means e raised to what exponent equals 28.4. I have no idea. I could hit it on the calculator if I want, but I don't care right now. I'm going to wait till the end. Okay, so I want to get x by itself, so I'm going to move this 3 over and add it. So I've got 2x equals natural log of 28.4 plus 3. Okay, this is not part of the natural log. I got to make sure I realize that. Let me just do this. And now to get x by itself, I'll divide by 2. So x equals natural log of 28.4 plus 3 and divide that whole thing by 2. So the reason I'm waiting till the very end to hit the calculator buttons is because then I don't have to keep track of this decimal number. And I'm not worried about it being off because I haven't rounded anything yet, right? People always say in math, keep things as exact as possible for as long as possible. Right? That's what I'm trying to do here. All right, but now I'm all done, so I need to go and hit some calculator buttons. So I'm going to put this inside parentheses. Make sure the whole numerator gets divided by 2. So I've got in parentheses natural log of 28.4, close that off, plus 3, end my numerator with parentheses, and then divide that by 2. There's my answer, 3.173. All right, let me give you guys one to try by yourself. All right, let me have you guys try and solve this one. I've got 400 equals 175 times e raised to the 0.12t. You guys go ahead and solve that. All right, so I need to isolate the base and the exponent. Let me just draw a box or a circle around that in yellow. I have to isolate that base and the exponent, so I need to get rid of this. And I'm multiplying by 175, so that means move it over here and divide. So 400 divided by 175 equals e to the 0.12t. Now you can divide this if you want and write it as a decimal. You can reduce it and write it as a fraction. Really doesn't matter. You know, think about quarters. How many quarters in $1.75? 7 quarters. How many quarters in $4? 16. So this reduces down to 16 sevenths. Or just leave it the way it is. There's nothing wrong with just leaving it like that. It's not my final answer, right? So I don't have to worry about reducing. I'm just going to leave it. That's the easiest. So now I need to take the natural log of both sides. So natural log of 400 divided by 175 equals natural log of e raised to the 0.12t. And I want to bring this down in front. So now what I have is natural log of 400 divided by 175 equals 0.12 t times natural log of e, which remember, natural log of e is just 1, and 1 times anything is the same thing. Eventually what people start doing is the moment they bring this down, they just quit writing this because they know it equals 1, and 1 times anything is that same thing. So I'm just going to draw a line through it. It's 1. So now to get t by itself, I want to divide by 0.12. So t is equal to natural log of 400 divided by 175 over 0.12. For those of you who don't like to show work, here's why it's so important. If you get to this point right here and I see this, I'm like, you know what you're doing. Even if the answer's wrong, you know what you're doing. You just hit a button by accident on the calculator or something. I don't know. Okay? But you got to that point, and it shows that we understand. You know, you probably only miss half a point. But if you don't show me this work and you've got the wrong answer, I can't give you credit for something I can't see. All right? That's why I keep on telling you guys, show your work. Always show your work. That should never change in a math class. All right? So now I'll hit the calculator buttons. I've got a natural log of 400 divided by 175. Got a close parenthesis, and then divide that whole thing by 0.12. And there's what I got, 6.889. So I don't know if you guys recognize this, but this is our Perk formula, right? And it's like saying if you had $175,000 that you invested at 12%, how long would it take to turn that into $400,000? Okay, now I know it doesn't say thousand there, but it's the same problem. You know, who wants to, I mean, yeah, if I put $175 in a savings account and I got 400 back in, what, 6.8 years, well, that's not bad, that's pretty good. You won't get that in a savings account, not in a bank, you won't. But if I went out and bought stocks that were paying 12% interest, and let's just say it was $175,000, in 6.8 years I could have $400,000. That's significant there. All right? So yeah, this answer, I chose T for time, about 6.9, so maybe close to 7 years, a little bit less than that. That's how long it would take to increase your investment to $400,000. That's more than doubling your money. That'd be pretty good. So let's do something that's more of a real life problem. And I want to look at the Perk formula. Okay, remember, this is an initial amount that you deposit, or think of it this way, it's an initial value of something. Anything that changes continuously, that's the starting amount, this is the ending amount. Okay? So I'm going to ask you a question about a car. I don't know if you guys remember this, I told you I would never buy a new car. I wouldn't do it. Doesn't make sense to me. Here's why. Alright, so I've got this problem. It says a new car costs $48,000 and depreciates at 17% per year. Now if you guys look at that and you go, geez Judson, what kind of car do you drive? I'm telling you, this is ridiculous. Spending that much money on a car. Unbelievable. When I lived in my house for 30 years. When I first bought it, I spent $68,000 on it. And now it's like cars cost more than that. You can easily spend more than this, right? My wife drives a Honda Pilot. We like it. It's a nice car. It's comfortable. It's a good ride. But a new one today costs about $48,000. So if we ever decided we wanted to replace our Honda Pilot, I don't want to spend $48,000. Forget it. No way. It's too much money. Okay? So here's what I want to do. I want to see how long it takes for that car to be worth $15,000. I'm willing to spend $15,000 on a nice used car. Okay? So how long does it take? And here's the thing. Cars depreciate on average at a rate of 17%. per year. How long will it take for this car to be worth $15,000? That's when I'm willing to go out and buy it. All right, so let's set this up. We've got, now remember, P is our initial value. So initially, in the beginning, this car was worth $48,000. It's depreciating, which means it's decreasing in value. So that means my exponent has to be negative. 0.17 times t. And I want to know, when is that going to be worth 15,000? All right? So right away I could say, let's divide both sides by 1,000 and get 48 and 15. There's just fewer things to write down, so it makes it a little bit easier. You know, but if you want to write 15,000 over 48,000, that's okay. It still works. All right, so I got to isolate my base and the exponent, so I'm going to move this 48 over and divide. So what I've got here now is 15 divided by 48 equals e to the negative 0.17t. I know I can reduce that, but I don't care. It's not my final answer, so I'm not worried about it. I'll just leave it that way. Okay, if you want to reduce it, you can go ahead and do that. It's okay. Just don't make a mistake. You don't want to make a mistake in the middle and have it affect your final outcome. All right, so now I'm going to take the natural log of both sides. So natural log, and so now I have the natural log of 15 divided by 48. I'm going to keep that in parentheses. I'll bring my exponent down in front, negative 0.17t times the natural log of e, which is 1. So I won't even write it down. I'm still going to write it down just so that we see what happens. That becomes 1. And so now to get t by itself, I need to move this over and divide. So t equals natural log of 15 over 48 divided by a negative 0.17. So I put that into my calculator. I've got natural log of 15 divided by 48 divided by a negative 0.17. You know, if you wonder how could that be positive, well, the natural log of this is a negative number, so we're doing a negative divided by a negative. But there's what I get, 6.842. T equals 6.842 years. All right. So, you know, you might look at that and go, I don't want a car that's 6.8 years old, almost 7 years old. Well, here's the thing. So, this happened, I think it was 2015. I'm driving down a road, and all of a sudden, I see this bright light, and then boom, a car smashes into me. Okay, my wife was in the car, my daughter was in the car. Our car got totaled. Right? I had to go out and buy a new car. So I had to buy a new Honda Pilot to replace our old one. And I found a car that was 7 years old. And it was traded in by some little old couple. I don't know who they are, but the guy told me. Some old couple traded it in. And I'm telling you, it was the cleanest car I'd ever seen in my life. You peel back the seats and there was no food in the cracks, you know, from people snacking in the car. The carpets were clean. I got underneath the car and looked at it, and it looked like it had never been driven in the rain. It was so clean. The car had 33,000 miles on it. It was 7 years old. Now, on average, most people drive 12 to 15,000 miles a year with a car. So 7 times 12, that's 84,000 miles. 33,000 miles. And I'm like, in my head, I said, I am not leaving this dealership until I have this car. So what I do is I go off with my phone, I start doing a little research. What was this car's worth originally? 17% depreciation. They wanted $22,000 for this car. And I went up to him and I said, look, everybody knows cars depreciate 17% a year. Nobody will argue that. So I do the math right there in front of them. This car was purchased for X amount of dollars at 17% depreciation. When it's 7 years old, it's now worth $17,000. and so I'll give you $17,000 for this car. Go talk to your boss. You know, because that's what they do. They go back and they talk to the boss behind the back door, and they come back and try to offer you something different. So he comes back and goes, can you do 20? And I said, no. Let's review. This car depreciates at 17% a year. Here's what it was worth originally. Here's what it's worth now, $17,000. That's my offer. So he leaves and he goes back and he comes back and goes, can you do 18? I said, why would I do 18 when it's worth 17? I will give you $17,000. I want to buy this car. Let's make this deal happen right now. The guy leaves, comes back, and he goes, all right, $17,000, it's yours. Pays to know something, right? When will you ever use math out in the real world? There's a great example of that. So I got a car that was 7 years old, but it only had 33,000 miles, so really it was like a 3-year-old car. You know, if someone did 12,000 a year, and it was squeaky clean. Now, I'm not going to say those kind of cars are available everywhere. You gotta do your homework. You gotta look for it and find it. But I walked out with that car. My wife was happy. She loved the color. You know, it was clean inside. It was her car that got totaled, not mine. I was just the one driving. But it wasn't my fault. Somebody ran a stoplight and barreled into the side of us. They were actually trying to beat a train across the railroad tracks, and they ended up totaling our car because of it. So yeah, this is good stuff to know. All right. All right, that's what we have for today. Let me get you guys a homework assignment. All right, so still week 16. This is Wednesday's piece. We're on page 254. We're going to do 29 to 53 odd. I think there's about 12 problems in there. All right. All right, you guys, there it is. That's what we have for today. You guys take care. Stay safe. I will see you on either Thursday or Friday. All right, bye.